In this lecture, I'm gonna be talking about another important article about contrastive self-supervised learning. And now we want to understand dimensional collapse, because we have two kinds of collapse: full collapse, that is collapse to a single point, which is the worst kind of collapse, or we can collapse into a subspace. We call it dimensional collapse. So this is a review of SimCLR, and I've explained this in a different video. But because it is important and it is a prerequisite for this lecture, I'm gonna be explaining it. So we have a picture, and then we have augmentation of that. So these are positive samples. We have a different picture because it's a batch size, so we need different samples inside a batch, and each one has different augmentation. So those that are from the same augmentation, they attract each other, like these one. But the other one are negative samples. So these are negative samples. They repel each other. So first we do augmentations for each element in the batch size. For example, 10 or 32 or 64 elements in our batch. We calculate the augmentation for an image, and from that we create representation, and then we maximize the agreement between them. So this is the first augmentation, and then the second augmentation, and we then calculate the pairwise similarity between them, and then we calculate the loss. Then we update the network F and G just to minimize the loss. So let's focus in this ICLR paper, which self-supervised visual representation learning aims to learn useful representations without relying on human annotations. Jointly embedding approach bases on maximizing the agreement between embedding vectors from different views of the same image. And various methods have been proposed to solve the collapsing problem, where all embedding vectors collapse to a trivial solution. Among these methods, contrastive learning prevents collapse for negative sample pairs. It has been shown that non-contrastive methods suffer from a lesser collapse problem of a different nature. For example, dimensional collapse, whereby the embedding vectors end up spanning a lower dimensional subspace, like this subspace, instead of the entire available embedding space. Here we show that dimensional collapse also happens in contrastive learning. And in this paper, we shed light on the dynamics at play in contrastive learning that leads to dimensional collapse. Inspired by our theory, we propose a novel contrastive learning method, which is called DirectCLR, which directly optimizes the representation space without relying on explicit training projector. So we don't use this projector. And the experiment shows that DirectCLR outperforms SimCLR. The self-supervised learning methods are useful in preventing complete collapse, whereby all representation vectors shrink into a single point. However, it has been observed empirically in non-contrastive learning methods that while embedding vectors do not completely collapse, they collapse along certain dimensions. This is known as dimensional collapse, whereby the embedding vectors only span a lower dimensional subspace. We're still not there, because in contrastive methods that explicitly use positive and negative pairs in the loss function, it seems intuitive to speculate that the repulsive effect of the negative examples should prevent this kind of dimensional collapse and make full use of all dimensions. However, contrary to intuition, contrastive learning methods still suffer from dimensional collapse. So there are two mechanisms for collapse. First, along the feature direction where the variance caused by the data augmentation is larger than the variance caused by the data distribution, the weight collapses. Even if the covariance of the data augmentation has a smaller magnitude than the data variance along all dimensions, the weight will still collapse due to interplay of weight matrices at different layers known, and this is implicit regularization. And this kind of collapsing happens only in networks where a network has more than one layer. So we empirically show that contrastive self-supervised learning suffers from dimensional collapse, whereby all the embedding vectors fall into a lower dimensional subspace instead of the entire available embedding space. We show that there are two mechanisms causing the dimensional collapse in contrastive learning. The first mechanism is strong augmentation along feature dimensions, and the second one is implicit regularization, driving models toward lower rank solutions. And this DirectCLR is a novel contrastive method that directly optimizes the representation space without relying on an explicit trainable projector. And DirectCLR, as I said, outperforms SimCLR with a linear projector. So this is the architecture, and you see that complete collapse is the worst collapse. You collapse in a single point. But still, dimensional collapse is a kind of collapse because you're avoiding different regions or different subspaces. So that's the embedding for info and CE, which is good for theoretical purposes. But we train the SimCLR model with a two-layer multi-layer projector. We follow that the standard method and train model on ImageNet for 100 epoch. Then, so this is a covariance matrix and singular value spectrum of that. And we evaluate the dimensionality by collecting the embedding vectors and validation set. Each embedding vector has a size of 128, and we compute the covariance matrix of the embedding. So we explained one scenario for contrastive learning to have collapsed embedding dimensions where the augmentation surpasses the input information. We focus on a simple linear network setting. We denote the input vector as x, and augmentation is an additive noise. And the network is a single linear layer with weight matrix, and the embedding vector is z. And we focus on a typical contrastive loss, which is called info and CI. And here z sub I are a pair of embedding vectors from two branches, because we have an image and we have augmentation of them. So z sub j indicates the negative sample within the mini batch, and when all zi and z sub I are renormalized to be unit vector, the negative distance can be replaced by the inner product. So this lemma says that the weight matrix is in a linear contrastive self-supervised learning model. It evolves like this, and G has this form where these are just the gradient and the embedding vector, and X is just the difference of positive semi-definite matrices. And here is a weighted data distribution, and this one is a weighted augmentation distribution covariance matrix. We need these lemmas because this theorem says with fixed matrix and a strong augmentation such that X has negative eigenvalues, the weight matrix has vanishing singular values. And then we can immediately say this corollary that says with a strong augmentation, the embedding space covariance matrix becomes low rank. So this is just a dimensional collapse caused by implicit regularization. So with strong augmentation, a linear model in influence CE loss will have dimensional collapse. However, such scenarios rely on the condition that the network has a limited capacity which may not hold for real cases. However, on the other hand, when there is no strong augmentation and X remains positive semi-definite, as a single linear model won't have dimensional collapsing. For deep networks, dimensional collapsing still happens in practice. To understand this counterintuitive phenomena, we start with the simplest over parameterized setting by choosing the network as two-layer linear multi-layer perceptron without bias. And the weight matrices of the two-layer linear contrastive self-supervised model evolved by this. So if W2 and W1 are aligned, then the singular values of the weight matrices under this info and CE loss evolves like this. So what is the main idea? We want to remove projector in contrastive learning by directly sending a subvector of the representation vector to the loss function. So we call this method DirectCLR. In contrast to all recent state-of-the-art self-supervised learning methods, our method directly optimizes the representation space. As you see in this figure, DirectCLR picks a subvector of the representation. So here you just pick a subvector. And a D0 could be a hyperparameter. And it applies a standard info and C. So the rest of that is just the standard info and C loss on this normalized subvector. And we train with a standard just 100 epochs on ImageNet. This figure shows why is the whole representation vector are meaningful in DirectCLR while only part of it receives gradient. So as I said, we pick only a subpart of that. So it takes advantage of the residual connection in the backbone. Thus the gradient passing through the representation vector is low rank, where only the first D0 channel dimensions are non-zero. When the gradient enters the ResNet backbone and passes through the last nonlinear conv block, it becomes full rank. Therefore, the hidden layer receives gradients on all channels.